Hi guys, today in day 2 of Calculator Bootcamp, we are going to be looking at CDFs and INVs. So we're going to be looking at NORMCDF, inverse norm, TCDF, and inverse T. If you don't already have the TI Inspire CAS app and you don't have a calculator that you've been using, I highly suggest you grab the CAS app from the App Store. It's free on the iPad right now up until I think the end of April. So make sure you go in and grab that so you have something to work these examples on, just so you can kind of follow along with me as we go through. I will give you guys the warning, today's video is a little bit longer only because I'm doing everything on the Inspire and then the 84, and in some cases I'm doing multiple examples. I'm really hoping that this is informative. Obviously, if you have just the Inspire, you can skip the 84 stuff, and if you have just the 84, you can skip the Inspire stuff. But let's get into it. Alright guys, today we're going to be talking about CDFs and inverses on a calculator, and today we're going to be starting with the TI Inspire. So the first thing I'm going to do is add a calculator page so that we can work through a lot of this. Now the first function we are going to talk about is one we've been looking at all year. This is NORMCDF. This one is great for finding the total probability under a curve, under a normal distribution curve from one endpoint to another endpoint. So I'm actually going to go through the menu on the first one so you guys can see what this looks like. So we'll go through the menu, go to statistics, go into distributions, and finally NORMCDF, normal CDF. So what this will let you do is set, we're without the CAS, okay. We're going to set a lower bound and upper bound, a mu and a sigma. Now, if you have the population statistics, the mean and the standard deviation for the whole population, this is pretty easy. Let's say we're talking about, I don't know, a golfer whose shots are normally distributed. Let's assume that his mean drive is 280 and his standard deviation is, say, I don't know, 40 yards. If we want to find the percentage of his shots that fall within 300 and 320 yards, for example, then we go up here, we change the lower bound to 300, and we change the upper bound to 320. And if we put this in, that will actually punch out a probability directly for his shots landing between those yardage. So what we did was we put in the lower bound, we put in the upper bound, we put in the mean, and we put in the standard deviation into that NORMCDF, and it kicked out a probability of about 15%. Let's try this again. This time we're going to go just typing it in, which you can also do on the Inspire. So we type in NORMCDF, 300, 320, 280, 40, and again it kicks out that same probability. Now this can be pretty handy because you can either go through the menus or you can go through the typing, whichever one kind of suits your fancy. Now for a second, let's imagine that we had first converted to z-score. So I'm actually going to demonstrate what this looks like on the calculator now. So we have our summary statistics, we've got that 280 for the mean, we got that 40 for the standard deviation. If you remember, the formula for z-score is going to be the number minus the mean divided by the standard deviation. So let's get our endpoints as z-scores. Okay, so we're doing 300 minus 280 divided by 40. So that's a z-score of half. And then we're going to do 320 minus 280. We'll just actually throw parentheses around it this time and divide. So that's going to give us a z-score of 1. Now the reason I'm showing you this is I want to show you how to do NORMCDF with the standard normal curve, which has a mean of 0 and a standard deviation of 1. This is when you're putting z-scores into it. So here, instead of the numbers we typed earlier, we're going to type NORMCDF. We'll put the 1/2. We'll put the 1. Then we put 0 and 1 as our two statistics. So again, this is when you have the z-scores and you're looking for the area between the z-scores, and notice it's exactly the same answer. So whether you're putting in z-scores or whether you're putting in the actual observations, that NORMCDF value should come out exactly the same. So now we're going to look at this same process on the 84. I'm still got my 1var stats open, so I'm going to quit out of that second mode. And we're going to look at how to use NORMCDF over here. Very similar process. So we'll go to stat, we're going to go over to, oh, I'm sorry, we're not going to stat. You actually need to press second and then vars. That'll get you to the distribution menu. From here, you can go to option 2, which is NORMCDF. So let's try exactly the same numbers that we just did. We'll put in 300 as our lower bound for this golfer's drives. We'll put in 320 as the upper bound for this golfer's drives. We use 280 as the mean, 280, I'm bad at typing on 84. And we'll use 40 as the standard deviation. And from there we can paste this, and it gives us that same probability. Now, on the 84, you can't type in just the word NORMCDF, which is fine, but you can still, if we go back to that distributions menu, use the z-scores. I'm actually going to calculate some z-scores first on here just so you guys can see what that looks like. So let's imagine we're calculating z-scores for our endpoints. We're going to do 300 minus 280 divided by that standard deviation of 40. That's 0.5. And we'll do 300 minus 320, minus 280 divided by 40. That's going to give us, 84. So we got to put both parentheses around that, and that should give us 1. From there, if you go back to your distributions menu, and you go to NORMCDF, you can put your lower bound as 1/2, your upper bound as 1, and now we're on the standard normal curve because we converted to z-scores, so the mean will always be 0 and the standard deviation will always be 1. From there we can paste this, and we get that same probability again. So in summary, normal CDF or NORMCDF works really well when you have a normal distribution and you're looking for a probability under that curve. Another really good use for NORMCDF is when you are dealing with proportions. Some of you might remember that whenever we're dealing with proportions, we are using the z distribution still, which probabilities are found using NORMCDF. So let's say, for example, that you are looking at a population where 55% of voters support a particular measure, and you're looking for the odds that say 6 of those voters would vote for that measure. So we're taking a random sample of 6 voters from a population in which 55% of voters support this measure. Okay, so we can actually calculate now our mean and our standard deviation. So let's go into the, we'll actually go right into the NORMCDF menu and do this directly. Alright, so statistics, distributions, normal CDF. So our lower bound, well, we'll get to that in a minute. And we're looking for the odds that, I don't know, let's say 50% of them support this measure. So we can start off by putting the lower bound, okay, let's say 50% or, I don't know, 50% or more. So we'll put our lower bound at 0.5 and we'll put our upper bound at 1. And I suppose we should probably put it at a very large number. And we're going to set our mu to be 0.55 because we know that in the population 55% of people support this. And then our standard deviation is actually going to be the square root of PQ over N. So in this case 0.55 times 0.45 divided by 6. And that should give us our answer. So there's a 59% chance that half or more of this sample of 6 voters would support that measure. We'll repeat this process on the 84, so we're going to go back into that distributions menu. Let's see if this works because I haven't done this on the 84 yet. And we'll go into normal CDF. Now remember, we're looking for the probability that half, well, we actually could have kept the half or more, so we make that a very large positive number, of this population where 55% of voters support some measure. So again, our standard deviation is going to be, let's see if it'll let us do this, the square root of 0.55 times 0.45, that's P times Q, Q being 1 minus P, we're dividing that by 6. Okay, from there, we'll paste that, and it does indeed work. So about 60%, there's about a 60% chance that a sample of 6 voters should have 50% or more support for this measure, given the statistics I already gave you. Okay, for our next question, let's imagine that we had some population of people where the average height was 5 feet tall or 60 inches with a standard deviation of 6 inches. And we're looking for the probability that a sample of 25 people has an average height of 70 inches. Okay, this is a great use of actually TCDF. Okay, because now we are working in the mean space. We're not totally sure that our population is normally distributed, but since we have a random sample of 25 people, it seems appropriate to use our T distribution. So let's go into this. We're going to go, let's see, to statistics, and then distributions, and then we're going to TCDF, not normal CDF. Again, T is great for means. So here, the trick is that we actually have to be in t-scores before we can go in and do this. So we're actually going to need to take a couple steps. By the way, because our sample was 24 or 25, we're going to use degrees of freedom 24. But before we do this, we need to actually calculate some z-scores. So remember, we're looking for the probability that in this group of 25 people, the average height is greater than 70 inches, even though we think that the population has an average height of 60 inches with a standard deviation of 6. Okay, so looking at this, we need to calculate first of all a z-score. So we're doing 70 minus 60, that's the observed height minus the population height. And then we're going to divide by the standard deviation. Now in this case, the standard deviation would be 6 divided by, let's see, where's my square root button? Square root of n, which in this case is 25, okay? So that should give us a t-score of 25 thirds, which is fine. We can actually go and put that in. So statistics, distributions, TCDF. Okay, our lower bound would be that 25 thirds, upper bound would be big number, degrees of freedom 24. Okay, very small probability that that sample of 25 people is going to have an average height that's that high. Let's look at this again on the 84, and I'm just going to demo the TCDF procedure with that 25 thirds number that we just looked at. So we go to second, then distributions, we go down to TCDF. Our lower bound would be 25 over 3. Our upper bound would be as big a number as we can muster. Degrees of freedom. Change workspace. Sorry about that. Broke the calculator for a second. But we want to go to second. Let's see. Where's distributions? We can go to TCDF. Okay. Our lower bound again would be 25 thirds. Upper bound would be a big number. Degrees of freedom will be 24, and we'll paste that. And that should give us the same odds. Yeah, very low probability that a sample of 25 from this population where the average height is 60 inches with a standard deviation of, I think I said 6 inches. Very low probability that we're going to get a sample of 25 people where the average height is 70 or higher. Okay, next up we're going to turn our attention to inverses. So on the Inspire, you can actually just type these, and the big ones that we're going to use are INVNORM, inverse normal, and INVT, inverse T. So for the first one, let's imagine that you have a normal distribution, and you're looking to see the z-scores that capture the middle, say, 60% of the data. So if we're capturing the middle 60% of the data, that means that 20% of the data should be below that and 20% should be above it. So you actually have two options here. And I'm going to show you both of these. Let's see if they make sense. So we can either do INVNORM, you can just type it in, on point 2, and I think you have to put in the mean and standard deviation as well. So what this is going to kick out is the value that cuts off 20% of the data below it, which is one of our endpoints. This should be negative, and it is. So a z-score of negative 0.841621 cuts off 0.2 or 20% of the data below it. Now, another way to tackle this problem is to think about, well, what value cuts off that top 20% of the data? To do this, you actually want to use INVNORM, and you want to go from 0.8. Okay, the Inspire and the 84 always go, I believe, from the left, although I think there's a tool in the 84 where you can actually go from the middle, and I'll show you that too. So we're running INVNORM here on the Inspire, 0.8, 0, and 1. Notice that gives us the same magnitude for that z-score. It's just that it's positive in this case. Okay, so in either case, the z-score is really going to be the same. It's just that in one case it's negative, in the other case it's positive. That's because you're cutting off either some percentage of the data below it or that same percentage of the data above it. Okay, so inverse normal on the 84. So again, we're going to press second. Oh, I'm going to press second on the 84 itself. Second, and distributions. And that's going to bring us to this menu. Now from here, we want to go back down, obviously, to INVNORM, which is number 3. Yeah, so this is what's cool. You can actually program where you want the data to be. So in this question, remember, we're asking about the area 0.6, so 60% of the area being there. If we have a mu at 0 and a standard deviation of 1, this is going to kick out a z-score. And I'm pretty sure we can actually do this at the center. So let's see what this gives us. Yeah, and this actually gives us directly the 2 z-scores. So this is a pretty cool tool on the 84 CE where you can have it give the 2 z-scores that cut off that percentage of the data in the center, which is actually something that the Inspire is not programmed to do. Kind of an interesting gap in the Inspire. If anyone figures out how to do that on the Inspire, please let me know. But as of now, I don't know a way to do it. So that's actually a way you can fast track using the 84 to get the z-scores that cut off the middle area of the data. Okay, last thing here, let's look at inverse T. So inverse T, of course, is going to do the opposite of what TCDF did. So just like how INVNORM gave us a z-score from a probability, inverse T is going to give us a t-score from a probability. So let's go into the menu for this one. Got to actually be on my Inspire window. Let's go into the menu. We'll go to Statistics, Distributions, and Inverse T. So this is going to work very similarly to the INVNORM. We're going to put in, let's say, an area of 0.2 degrees of freedom. So this is where things can change. Let's give ourselves a nice big sample. So we'll say we had a sample size of 50. And then we'll hit OK. And you'll notice this is going to give us a very similar t-score to the z-score we just got. Now, of course, we can do this inverse t the other way as well. We could go 0.8 instead of 0.2, and that should give us the positive version of that t-score. Okay, let's look at this finally on the 84, and this is going to be the last thing we look at today, this inverse t on the 84. Okay. So here we're going to go to second distributions. We're going to go down to number 4, which is inverse T. And here we have to put in just the area and the degrees of freedom. Interestingly enough, and unfortunately, the 84 doesn't offer that center mechanic like it does in INVNORM. But that's fine. We just have to do a little more thinking. So remember, we're looking for the values that cut off the middle 60% of the data. So they either cut off 20% below, meaning an area of 0.2 with degrees of freedom, we said 49 in the last one. And there we go. We could also think of this as cutting off 0.8 and 49, and that's going to give us the positive value of that. Okay, so I'm going to wrap here. We covered in this video NORMCDF, we covered inverse norm, we covered TCDF, and we covered inverse T. And those are the 4 big CDF and inverses that you really want to know on the calculator.